can move on now to the next speaker, who is Tina.
Yes, hello. Let me share my screen. Okay. Oops. All right, are you able to see my screen?
Yes, that's looking great. Please go ahead.
Okay, thank you. So like Tess, I did this study during my PhD about 3 years ago, where we basically wanted to understand the spatial biases and uncertainties in the global fire emissions inventory. So we looked at 5 emissions inventories: GFED, GFAS, FIN, QFED, and then we looked at Indonesia in particular as a regional case study. So to give a bit of a background about Indonesia, basically during El Nino years, there's a suppression of convection, which leads to very dry conditions over equatorial Asia. And you get these fires that are associated with land clearance and agricultural maintenance practices, usually on a lot of concessions areas, such as for oil palm or logging. And then these lands are often on areas with peatlands. So when the water table drops down, the peat is very susceptible to fires. And if the fire burrows underground in these areas, these fires can burn for days to weeks, and they're very difficult to extinguish. And when you get these fires in peatlands over the region, you have very severe haze that blankets the entire region in these years. And this leads to very high concentrations of PM 2.5, which leads to increased premature mortality. And I also wanted to give some more background. So I'm going to talk about a study that we did looking at both land cover change and fires and how that leads to public health impacts. So fires actually occur in Indonesia every year, but because of the conditions associated with El Nino, this becomes very hazardous in these years. And you can see in this image here, this year, there was a lot of smoke and fires. And also other years that were associated with high fire activity were 2015 and 2006 and 1997. And after the 2015 fire season, Indonesia created the Peat Restoration Agency to restore the hydrology of these degraded peatlands to try to mitigate the amount of fires in subsequent fire seasons. And it's very important to account for the public health impacts related to the smoke across the region, not only in Indonesia, but also Singapore, Malaysia as well. So in previous studies led by Shannon Copeless, Marion Marlier, we have the scientific framework using fire emissions along with information about land use, land cover, and also geochem as well to try to estimate the public health impacts. So what goes into this framework is we used land use and land cover from Margono and also peatland information to try to come up with these different land cover categories. So we had intact forest, degraded forest, non-forest, and plantations and secondary forest. And we used GFED to relate the land cover and fire emissions rates. And then we ran geochem, the adjoint, which relates the sensitivity of each grid cell to the receptor. And we essentially multiplied the adjoint sensitivity by the fire emissions rates to get the smoke PM 2.5 at the receptor. So we looked at the population-weighted effects in Indonesia, Singapore, and Malaysia. And then finally, we used the model smoke PM 2.5 to get the concentration response functions. So what this looks like is First, we had the land use and land cover information, and this map shows the different land cover categories that we used. So on the top here, I'm showing the intact forest, degraded forest, non-forest, and plantations and secondary forests. So this was derived from both the Margono data set for Indonesia, as well as the Hansen forest cover data set. And then we also related the peatland locations with the land use and land cover information. And secondly, we use the GFED emissions inventory. For these years, we related basically the average fire emissions rates associated with each land cover type. And then third, we use the GeoSchem adjoint. So these three maps show the average sensitivity of fires to that receptor. So for example, in the top panel, I'm showing the adjoint sensitivity for Singapore. So the colors were, it's warmer, redder in color. It shows basically in Sumatra on the east coast here and also southern Borneo that if fires occur in those areas, Singapore would be very sensitive to smoke release from those regions. And so we multiplied the adjoint sensitivity by the fire emissions in order to get the smoke PM 2.5 at these three receptors. And here I'm showing the smoke PM 2.5 observed in Singapore and also modeled from our approach. And then finally, using the smoke PM 2.5 and concentration response functions from metadata analyses, we're able to calculate the public health impacts from these fires in these three receptors. And we also looked at different land use scenarios. So what happens to the smoke PM 2.5 and premature mortality if, for example, we remove fires from peatlands? So if there was increased restoration activity in the future, how that would affect the fire activity and the smoke exposure. So the majority of fire emissions are from peatlands. As you can see here on the left, that about 2/3 of the emissions are occurring on peatlands. However, in terms of area, peatlands only make up about 9 to 17% of the area. So peatlands are a very important source of emissions in this area. And then, so because we only use one fire emissions inventory in that study, I then wanted to look at different fire emissions inventories and how they differ. So previously, various studies have quantified the public health impacts from Indonesian fires, but actually each of these studies use different fire emissions inventories. They also use different atmospheric models and different health concentration response functions. So in order to understand these different estimates, here we wanted to examine the different fire emissions inventories used. So this study was published in 2020 in RSE. So here I just show the differences between these three studies. So for example, in Kripa et al., they use FIN version 2. In Coplitz, we use GFAS version 1. And then in Marlier et al., we use GFED version 4S. They also use different chemical transport models and then ended up with different public health impacts as well due to these differences among the studies. So as Tess mentioned, there are the bottom-up inventories and the top-down inventories. So for the bottom-up inventories, we examine GFED version 4 and FIN version 1.5. For the top-down inventories, we used GFAS, QFED, and FEAR. And these are the versions that were available at the time, but I realize now that FIN has 2.5 now, and GFED will be moving to version 5 in the future as well. but hopefully this will give you a sense of the differences between these inventories. So for the bottom-up inventories, they use burned area estimates, and for the top-down inventories, they mostly use FRP, which is converted into fire energy. And as Tess also already mentioned, these are the equations for the two different approaches. And so then we just wanted to look at the differences between the inventories. For example, they have different resolutions. They have different near real-time availability, different satellite fire inputs. Some of them accounted for peatlands, but not others. Some accounted for cloud gaps and fire detections. And then others also accounted for scaling of aerosol emissions using AOD. And globally, we just looked at the differences between the total emissions for different species. You can see, for example, if we look at OC and BC, that the top-down inventories, namely QFED and FEAR, have much higher estimates than the bottom-up approaches, including GFED and FIN, and also GFAS as well, which was calibrated using GFED. So here are the differences for the different regions. So for example, if we look at on the bottom here, where I've highlighted Equatorial Asia for Indonesia, they actually have pretty similar annual OC plus BC emissions. But then if we look at the interannual variability, they actually have very different variability there. And then if we look at other regions, the different inventories have a lot of differences in just the total amount of OC plus BC, for example, in North America, as Tess mentioned in her presentation, that QFED had much higher emissions than the other inventories. So for our study where we looked at Indonesia in particular, we had the adjoint sensitivities for 2005 to 2009, and we used rainfall rates over Sumatra and Kalimantan to just use those adjoint sensitivities for other years so we can compare the PM 2.5 in those years as well. So we just picked the nearest rainfall rate from years from 2005 to 2009. And then, as I mentioned before, basically the approach is we multiply the adjoint sensitivity by the fire emissions in order to get the smoke PM 2.5. So this is showing the smoke PM 2.5 that's observed and modeled using the different fire emissions inventories. The dots show the ground observations in Singapore, and the lines show the modeled smoke PM 2.5. So you can see among the different inventories, there are some inventories like GFED and GFAS that match pretty well with the smoke PM 2.5 in Singapore. But for others, they're way too low in some years or pretty high in other years. For example, if we look at 2015 on the bottom here, which shows the July to October mean, that GFED and GFAS approaches the observed PM 2.5, but the other three inventories are way too low compared to observations. And one issue is that only GFED and GFAS at that time considered peatlands as a distinct land use and land cover class. For FIN later, for version 2 in the CRIPA study, they did account for peatlands, but here in version 1.5, peatlands were not included. So this was one main factor that showed the difference between these inventories. In particular, peatlands have much higher fuel consumption rates and emissions factors for these species. And for this study, I also created the FireCam online tool. So I basically uploaded all of these inventories to Google Earth Engine, which is a cloud computing platform. And I made this online app so that users can quickly compare the differences between emissions in different regions. So here we're showing the Indonesia fire emissions for the five fire inventories. So it shows the annual and monthly and time series of fire emissions there. And you can also look at different species, including OC, BC, CO2, and CO as well. And for version 2, I'm planning to update it with GFED 5 and Fin version 2.5 and newer versions of the other inventories as they become available. And especially since we're moving away from MODIS-based inputs to VIIRS-based or Landsat or Sentinel adjusted emissions estimates as well. And there's also a companion tool called Smoke FireCam, which provides an example of the Smoke PM 2.5 that's estimated from these fire emissions inventories in Singapore, Malaysia, and Indonesia for Indonesian fires. So how can we make sense of these different biases and uncertainties in the fire emissions inventories? And the goal is to allow end users to rapidly understand these biases and uncertainties. And with Google Earth Engine, we can make use of the efficient cloud computing power with big geospatial data sets in order to create very simple metrics that might allow an end user to quickly compare these different inventories. So for example, we can look at the difference between the burned area versus the active fire input. We can look at clouds and thick haze, which might obscure observations of fires. And we can look at small and fragmented fires versus large continuous fires. In general, burned area products tend to do pretty well for large fires, but the active fire products tend to do better for the small and fragmented fires. And then we can also look at topography as another metric. And for very small fires, this is just using VIIRS to look at fires that are outside of the MODIS burned area or active fires. So for one example, we looked at cloud cover and thick haze as a metric. So this was derived using the MODIS surface reflectance. So the index here show the surface obscuration, where 0 is more clear conditions and 1 is more cloudy and hazy conditions during the fire season. And here I've highlighted Indonesia, which shows very cloudy and hazy conditions during the fire season. And then we can say, for example, during the fire season, Indonesia's land surface is obscured by clouds and thick haze, which makes it very challenging for satellites to detect fires. And the inventories that adjust for these gaps tend to do better in terms of accounting for the variability in emissions and also the magnitude of emissions as well. So we found that GFAS, because it both accounts for peatlands and also these cloud and haze gaps, that it captures fire activity the best in this region. And here I'm showing the correlation between rainfall rates and active fires, burned area, as well as AOD and FRP. Because rainfall rate is very highly correlated in the log-log space to AOD, we wanted to look at 2015 in particular, because that was a very severe fire season and how that fire year lined up in this relationship. So as we can see that for AOD, it's pretty correlated, but then if you look at active fire count, burn area, and FRP, 2015 is actually lower than what we expect. So that means there's a lot of smoke and thick haze, which probably obscured a lot of fire activity and led to underestimates in either active fire counts or burned area. So for my take-home message is that for Indonesia during dry years, there's high fire activity in Indonesia, which leads to extreme haze over equatorial Asia. and about 2/3 of the fire emissions are from peatlands. So that makes peatlands very important for accounting for fire emissions in this region. There's a lot of challenges associated with fire detection in this region related to high cloud cover or dense smoke cover. And then the presence of a lot of these cool smoldering fires on peatlands. And we also saw that the choice of the fire emissions inventory can significantly impact the model smoke exposure and public health estimates. In particular for Indonesia, it's very important for inventories to account for the high fuel consumption in peatlands and also the cloud and haze gaps in fire detection. And we also devised some simple metrics to help end users understand the regional differences between these inventories. And you can check out the FireCam tool if you want to quickly compare the fire emissions in these different regions. And I will say that the choice of the fire emissions inventory differs a lot based on which region you're looking at. So for example, for Indonesia, GFAS might be the best inventory. But if you looked at another region, for example, like Northwest India, GFAS is actually one of the worst inventories because it severely underestimates the fire emissions in that region. So for your area of interest, it's pretty important to first get a sense of the differences between these estimates and then to understand why these differences are happening. But I'm happy to take any questions related either to Indonesia or to the differences between the inventories.
Thank you very much for that, Tina. So we have plenty of time for questions again. Guido has a hand up.
Yeah, thanks a lot for the talk, Tina. I mean, such an interesting region, and also thanks for making that the website available. I think it's very useful for a lot of us. A question: have you looked into 2023? Because you mentioned the restoration projects. I mean, it's been an El Nino. I mean, there's more fires than normally, but it's nothing compared to, for example, 2015. Do you have a sense that the restoration projects helped?
Yeah, so I haven't really looked at Indonesia after 2015, but in 2019 and 2023, there were higher fire activity than expected because of the El Nino conditions. I think restoration might have decreased the number of fire counts, but I haven't specifically looked at those recent years. And for our original study, we did have the locations of the restoration areas. So for that study, we basically said, using our estimates, these areas are very important for peatland restoration. And so the tool actually calculates where areas are most important for decreasing the amount of smoke exposure. But yeah, I think one important study for the future is to look at whether the restoration actually made an impact on the smoke exposure in the region. But thanks for your question.
I see Cindy has a question in the chat there. Do you see that, Tina?
Yes, so I can read out the question from Cindy. Cindy says, surprising that QFED was low for PM 2.5, but high for BC plus OC. But I guess this was because of the lack of peatland fires. As you mentioned that GFED and GFAS include peatland emissions. Do more recent FIN 2.5 and GFED version 5 include peatlands now. And then she also said the tool for examining uncertainties against different metrics, is that the same as the FireCam tool or a different tool? Yeah, so the first question is QFED is actually low for both PM 2.5 and BC plus OC. And as you correctly said, this is because of the lack of peatland fires. But I think in the future, QFED will include peatland emissions. So I think this will be fixed in the future. And then GFED and GFAS include peatland emissions. I'm not sure about FIN version 2.5, But I know in the Fin version 2 that the CRIPA study used, they did account for peatlands in that version. And then the tool for examining uncertainties. Yeah, so the FireCam tool both lets you look at the variability and emissions for different regions, and it also has the different metrics already embedded in the tool. So you can click on the different layers for the metrics and then also compare that against the magnitude of emissions. And yeah, Guido says GFED 5 will still include peatland emissions, and now also for the boreal region as well. So that's really good to hear.
Right, so we would still have plenty of time for questions, up to 10 minutes if you have any more.
Yeah, I will mention one thing is that for a lot of atmospheric chemists, for including these inventories, it costs a lot of model runs to look at kind of just to get a sense of the range of smoke PM 2.5. So with the FireCam tool, it's kind of a quick way to get a sense of that difference. And Christine said, we have 2 studies that included peat fires in equatorial Asia. However, the methods that were applied are not in Fin version 2.5 and is something they're looking at into the future. Thanks, Christine.
Mark also has a comment there, which you can all read, but I see that Terry has a hand up. Terry, please.
Yeah, Tina, I'm just going to ask you the same question I asked Tess earlier, and it seems like you've done a lot of the work to evaluate and provided some criteria by which we can evaluate different inventories in different regions. And so I'm wondering, how close do you think we are at being able to produce sort of an ensemble or best estimate by combining inventories from different regions?
Yeah, so I would say that for each region, there's a lot of region-specific differences. So the choice of the inventory might be substantially different as you move from region to region. But yeah, in terms of that, I think we're still a little bit far off from just having that ensemble. Of course, you can look at the different fire inventories and provide the range of estimates. But then there still needs to be that understanding of what's causing these differences between the fire inventories. And then for different regions, there might be different factors that are important. For Indonesia, peatlands are really important, but that's not the same for North America or India, for example. So there needs to be a lot more, I think, region-specific studies that look into these differences and explore the causes for these differences. But yeah, thanks for your question.
Thanks.
Yeah, thanks for that, Terry. I was also wondering about how well that tool you have, Tina, could be used for something like creating a mosaic of fire inventories, and also just wondering whether doing that by region is the best approach, right? Is it that some, as you mentioned in your answer as well, is it that some products are better in particular regions, but they're better for particular reasons? Maybe a mosaic could be done based on the vegetation type from each product, or the kind of fire from each product, rather than specifically looking at regions, or is that getting way too complicated?
Yeah, I think that's a really important point to look at the land cover, and also I think fuel consumption estimates between the different inventories also matter a lot. So for the metrics, we mostly looked at the difference in the fire data sets that are input into these inventories. But for Indonesia, we found that, for example, Fin had much higher fuel consumption than GFED, and that led to the bulk of the difference in magnitude between those inventories. So yeah, I think one important factor is to look at the differences between the fuel consumption kind of estimates used in these different inventories too. Yeah, and Cindy also said, and better for particular species as well. Yeah, I think in particular for accounting for the aerosol species, for example, QFED and FEAR use additional scaling for those species. So that led to higher estimates compared to the other inventories.
Yeah, I guess I had maybe a silly question on that as well. I'm not an expert at making fire emission inventories, but when something like the aerosol species is scaled to the observations, basically doing an inverse approach there, but the other species are not, does that lead to maybe species emission ratio? So example of BC to CO ratio or something that you would never actually observe in a real fire. Is that a thing?
Yeah, I think usually we would look at those separately. So CO, for example, on its own, or OCMBC on its own. So for these studies, we mostly focus on the OCMBC because it's most related to the public health impacts that we wanted to explore. But for those studies, we also adjusted the final PM 2.5 relative to the observations. So there is a scaling there that tries to match our modeled observations with the or modeled estimates with the ground observations.
Yeah, this has a comment there.
Yeah. Johanna said, I agree that separating the effects of different fuel consumption and emissions factors and emissions of individual species is needed to understand the differences.
Well, I'm not seeing any more comments, questions, or hands. So in that case, thanks again, Tina, for a great talk.